last lecture of this workshop, and this is also the last of the 4-lecture series by Sir Michael. We saved the best for the last. And, the title of the lecture is Real Differential Operators.
Right, thank you. So this talk, I'm going to talk about real differential operators and explain what's interesting, what the problems are, and the talk will have 3 parts. In the first part, I'll explain what we mean by real differential operators, why there is an interesting problem, what interesting things there are to calculate. This will lead me on to introducing the right kind of K-theory that has to go with the real differential operators. This is a new kind of K-theory, and I'll explain a little bit why this new kind of K-theory is actually very good by itself, and you can use it as a new foundation to develop K-theory. And then the last part, the lecture will be 2 examples, of interesting examples of things which are real operators in the index theory, which have interesting applications either in topology or in algebraic geometry. So that will be the way the lecture will be divided. So first I'll talk about real differential operators. Let's see, how's the focusing going? Is it okay? Can we dim the lights again? Who is the expert on focusing here? Or is it okay? Well, no, that's better. Okay, that's probably it. Thank you. That's good. So a real differential operator, it simply means that you write down partial derivatives with real coefficients. Naive way. But at first sight, it doesn't look as though there's any interesting theory which you can develop, because if you want to calculate the index of an operator, it's an integer, and if you calculate, there's no difference calculating the dimension over the real numbers and the complex numbers, it's the same integer. So what is the advantage? Why do you need to do anything more for real theory? Well, here is one explanation. When you develop this index theory for operators, you can do a more general, in general, for complex operators, you can do a more general theory, which is to study the theory with parameters. So if you have an elliptic operator that depends on a parameter continuously, and the parameter belongs to some space, capital Y, then you can define the index, which is not just an integer, but is an element in the K-theory of Y. And roughly speaking, the idea is the following. Along the fibers, every operator is elliptic. It has a kernel and a co-kernel. As you vary over the point in the parameter base space, the parameter space, the kernels, so to speak, in general will form a vector bundle, family of vector spaces. The co-kernel will form a family of vector bundles, and the index will be the difference of those 2 vector bundles. And the subtlety is that, in general, when you vary the parameter, the dimensions of the null spaces can jump around, but even when that happens, the co-kernel also jumps around. Not only is the integer index invariant, but even you can smooth out to make the element in the K-theory well defined. So the K-theory gives you a natural home for the indices of families of elliptic operators. That's general, and the index theorem you can go give formulae which will calculate this. Now, if you have a real operator and a real family, then, according to the same philosophy, the answer should be a vector bundle on the base space, which is a real vector bundle. So you should get the real K-theory, which is usually called KO, O standing for the orthogonal group. Now, real K-theory on a space, which is more than a point, it maps to a complex K-theory, but this map is not always injective. So if you go to the complex theory, you lose some information. For example, if Y is a circle, so we're just considering a sort of periodic family of elliptic operators, which are real, then the real vector bundles on the circle include, of course, the trivial line bundle, but also there is the non-trivial line bundle, which corresponds to the Möbius band. You go around 1, and it comes back multiplied by -1. So the K-theory of the real K-theory of the circle is the integers corresponding to the dimension plus the integers modulo 2, whereas the complex K-theory has only the integers. And so when you go from the real theory to the complex K-theory, a certain Z2 is lost. And you would like to get this information in a way which is natural. That is why you need a real theory. You'd like to not lose the information that is contained in there. By the way, the difference between the bundles on the circle, the real theory and the complex theory, has, of course, to do with the difference in the topology, also of the orthogonal group and the unitary group. Now, so this leads me to the general question of also another reason for needing the real theory is to do with invariance modulo 2, which are called mod 2 indices. Now here we don't need to have a family, just a single operator. But if you have now, so if you have an operator, T, let's say, elliptic differential operator or abstract Fredholm operator, if it is real, so it acts on a real Hilbert space if you like, and is skew adjoint, so T star is minus T. Of course, the index for this operator is always trivially 0 because the kernel of the operator and the co-kernel, co-kernel is the index kernel of the adjoint. The adjoint is the same operator up to sign, so we get cancellation and index is 0. That's not interesting. But now there is interesting invariant modulo 2, because a skew adjoint operator, which is elliptic, will have discrete eigenvalues, and these eigenvalues, if it's skew adjoint and real, will be complex conjugate pairs of the form plus or minus I lambda, where lambda is real, just like with ordinary matrices. And as you vary the operator, the reason that the null space can change in dimension is that an eigenvalue can go to 0. But if lambda goes to 0, minus lambda goes to 0. So the dimension changes by a multiple of 2. Therefore, the dimension of the null space is unchanged under perturbation. So for a real skew adjoint operator, the dimension of the null space modulo 2 is a topological invariant. And we call this a mod 2 index. It's analogous to the index we had before, and in fact is part of a general theory which combines everything. So this is an example of something we would like to calculate, and the example I will give at the end of the talk will be of this kind. Now actually there is a link between this is index here for a single operator and the index for a family of operators I described before, parameterized by the circle. If you have a skew adjoint operator like this, then you can convert it into a family of operators on the circle. You write down t theta, cosine theta plus t sine theta, going between 0 and pi, so it connects plus 1 and minus 1 in the complex plane by a semicircle. It moves away from the skew adjoint operators in the big space, so you end up with a family of elliptic operators over the circle, and that the bundle over the circle you get is either trivial or non-trivial, and that's the mod 2 invariant appearing again. So the two things are actually linked by the general theory of a family will include the other one, but the examples come naturally also directly for a single operator. Now that's the first example of a mod 2 index, but there's another one, very similar, which is the following. Suppose now I have an operator, again, elliptic differential operator or Fredholm operator, and this time it is acting on, if you like, the underlying real space of a complex space, but it anti-commutes with R. So instead of being complex linear, it's antilinear. Also, it's still skew. Now this time, because it anti-commutes with I, the null space will be acted on by I. So the null space is automatically, so to speak, complex, will have even dimension. So the mod 2 index we talked about before would not be interesting. But now, if you look at the other eigenvalues, the other eigenvalues will actually turn out to have a J in them, which will, coming from this, you see, if you have a skew adjoint operator, then other eigenvalue you'd have you'll have eigenvalue lambda. If you normalize them, there'll be elements of square minus 1, which anti-commute with I, so they'll give you rise to quaternions. So that means the dimension of the null space thought is complex, but the parity over the complex numbers is topological invariant. If you vary the parameters, it can jump by quaternion spaces, in spaces multiples of 4, real dimensions. So this is very much the analog of the previous one, except that you work the difference in between going from real numbers to complex numbers before. Here you can now go from complex numbers to quaternions. And so now it turns out, in general theory, these are related to the topology of the orthogonal group. The orthogonal group, ON, has two components given by the determinant, the sign of the determinant, orientation preserving or reversing. The two components we call pi 0, the zeroth homotopy group. That's integers modulo 2. But it is not simply connected. It is double covering the spin group, which is of order 2. And that's the second one, that's pi 1. And these two different integers modulo 2 correspond to the two types of indices modulo 2 I've given you above. And you can compare, I say 2 is the fundamental group, the orthogonal group is Z2, whereas the fundamental group of the unity group is the integers, which gives rise to the integer index. So all of these indices have their origins, if you like, in the topology of the linear groups. And the whole game is to exploit that and use that to provide formulae. So there are interesting problems in analysis which involve invariance, topological invariance, modulo 2, which we would like to be able to understand. So we'd like to develop a theory for this. Now, the answer is that if you try to apply the real theory of vector bundles we have to the index problem, it doesn't seem to work. It gives the wrong answers. So you feel that something is missing. And when you think about it more carefully, you find that actually is a better definition of real K-theory than we had before, but it doesn't just consist of real vector bundles. And the two clues to tell you what to think about are the following. The first clue comes from thinking of the Fourier analysis. When you take a function and write a Fourier periodic function, write the Fourier coefficients, here is now there 1 over 2 pi integral around the unit circle of eta I n x. The Fourier coefficients, an, if the original function takes real values on the circle, then the Fourier coefficients are not real. But a minus n, is the complex conjugate of an. Easy to check from the definitions. So you see, something which is naturally real as an operator is Fourier coefficients have a different definition of reality. It corresponds to conjugation in changing the sign. And the same thing is true for Fourier transforms, a function of the line. Instead of having the Fourier coefficients, then you have the Fourier transform function, and you have another variable psi, which and the property there is the complex conjugate. You change psi to minus psi. So that's one indication that we should do something different. Another indication is from algebraic geometry. If you are dealing with algebraic geometry, affine algebraic geometry given by polynomial equations in complex space, then there always is associated to affine variety the coordinate ring, the ring of functions, the polynomials in the space modulo the ideal that defines the variety. And the language of bundles on affine varieties in algebraic geometry is well known to correspond to a purely algebraic language about the algebra, the ring, the coordinate ring, A of x. And a vector bundle corresponds to what's called a projective module over the ring, a direct summand over a free module. Now, if the algebraic variety is defined over the real numbers, that means given by polynomials with real coefficients, then what the algebraic geometers do is they don't just look for the real solutions. For example, the equation x squared plus y squared equals 0 has no real solution except 0. Or you take x squared plus y squared plus 1 equals 0, has no real solutions at all. So looking at the real solutions is not very good. What you do is you look at all the solutions, the complex solutions, but then you observe that since the equation is defined over the reals, you can every point on the variety, you have a complex conjugate point on the variety, another point. And this is complex conjugation of the complex conjugation preserves the set of zeros because it's defined over the real numbers, and that is the way to look at the real algebraic variety. Now, correspondingly, the modules, the vector bundle, should correspond to a projective module, and now we have a perfectly well-defined ring over the real numbers. Sorry, R here. Yes, the ring A of x is now defined over the real numbers in R algebra over the real numbers, and you can talk about projective modules over the real numbers. So a projective module over the reals is really what you think of as an algebraic vector bundle over a real algebraic variety. And what it means is that you take all the complex points in x, on there is a complex conjugation, and what the projective module does is it gives you a vector bundle on x, which is itself a complex vector bundle, and a conjugation that covers the conjugation on the base space. And that will turn the fiber over a point x. It will map it antilinearly to the fiber of the point of x bar. That's the natural definition of a vector bundle in real algebraic geometry. So you see, in both cases, the way the real numbers sort of manifest themselves, if the real numbers appear as coefficients of the differential operator, or as coefficients of the defining polynomials, the way the reality condition comes in is through the complex conjugation being fitted into the geometry. So with those key ideas, then we can naturally lead to think of the following definition of a real K-theory. So now we want to move away from algebraic varieties to general manifolds. So we're doing not algebraic K-theory, but topological K-theory, but we use our motivation. So we'll suggest that a real topological space X, we'll call it a real space, just to have a nice little word for it, if it's a space which has an involution, map of order 2, which we think of as complex conjugation. If it's an algebraic variety of the complex numbers, this would be complex conjugation. But it need have nothing to do with algebraic geometry. And a real vector bundle, in this sense, will mean a complex vector bundle over the space X, together with an antilinear map on the vector bundle that covers the map on the base space, just like in real algebraic geometry. So if X is a real algebraic variety, then this would correspond to a projective module over the coordinate ring, exactly what we have. And this definition of a real space and the real vector bundle will naturally lead you to develop a Grothendieck group and get a KR theory, which you'll call KR. Fortunately, real vector bundle before led to a theory which is called KO, so R has been left free. We can use it now. And so it's very convenient. So KR theory is defined this way. It's a very natural and a new theory. It wasn't considered before. So we start from scratch to develop the theory. Notice that if the involution on the space is trivial, if every point is fixed by the involution, then that means that on the vector bundle you have this antilinear map in the same space. And that means that the vector bundle really is the complexification of a real vector space. And so if the involution is identity, then KR of X is just what we call KO of X, this real vector bundle. So it includes the ordinary case when there is no involution. Now, if you now bring in the complex numbers as a space, two-dimensional R2, then we will always give it the standard involution, complex conjugation. And now we go back to the elementary proof of the periodicity theorem, which I gave in the first lecture, and which I also mentioned yesterday. The key fact there, you remember, is that we used approximated functions on the circle by finite Fourier series, Laurent expansion. So we see immediately the complex numbers coming in with the unit circle, and we see the Fourier coefficients. So it's not too surprising when I tell you that the proof I gave of the periodicity theorem works word for word in this theory KR, so long as you give the complex numbers the involution of complex conjugation. X will have an involution given to you in advance. You naturally extend that with the complex conjugation on C, and the periodicity theorem just says that this is isomorphic to that. Here I'm talking about K theory with compact. X is a compact space, say. C is not compact, so we take K theory with compact supports, which means, if you like, you compactify the complex numbers by adding a point at infinity, and then you work modulo the point at infinity. You throw away the trivial part. Anyway, this periodicity theorem works word to word with the proof I gave before, and so you get a very nice theory developing. So we now start to look at that theory, and in particular, you go back to why we introduced it. If you start off now with a real elliptic differential operator, then its symbol, I described to you, was described by the highest order term in the operator, as an invertible matrix, and it was defined on the cotangent bundle of X, and it was given by an isomorphism outside the zero section, which could lead you to an element of K theory of compact supports of the cotangent bundle. Now, if you work with a real differential operator, you'll end up naturally in this KR theory, in which the involution on the cotangent bundle is defined to be -1 on the fibers. Even if there is no involution on X, you make it act on the fibers by -1. If it's an involution on X, you also add the -1 to the fiber as well. And the reason for that, well, first of all, when you took the symbol of an operator, I told you you got by replacing the partial derivatives formally by variables, cotangent variables. But from an analytical point of view, it's natural to use I times d by dx, because d by dx is skew adjoint, the I term is self-adjoint, corresponds to multiplication by a variable xi. In Fourier transform language, it's I d by dx that you have to use. And that's why the complex conjugation in I corresponds to -1 in xi. So if you like, the left-hand side is Fourier theory, the right-hand side is algebraic geometry, and by this transformation they match. So it fits in all very well. And if you do that, and develop the theory, and you get if you have a theory parameterized by a parameter base y, then you go through all the machinery, and you will end up with index in this KR of y. So we've got into the refined theory that we wanted. If now y is an ordinary space, then this is same as what I had before. But it's not an ordinary space. It's if y. The involution if you have a family can act on the fibers, it can also act on the base. So Y could be a space with its own involution, or it could be a space with a trivial involution, and you only act on the fibers. If Y is a space with a trivial involution, so you only act on the fibers, then the answer lies in the KR of Y, but because the involution on Y is trivial, that would be the same as the KO theory of Y, which is the real K theory. But that isn't always the case. So this gives you, so shows that this is the right kind of theory to apply, fits in the gap in the theory of elliptic operators, and everything works well, and the problem is solved as far as finding a topological way to describe the interesting invariance for real elliptic operators. But now, having introduced this KR theory, we should look at it topologically a bit by itself. The Bott periodicity theorem is a fundamental theorem. It still works, but there is more to it than that. So this way you can write and develop this topological theory, forgetting all about analysis, forgetting about algebraic geometry, forgetting about elliptic operators. Just look at it as a topological tool, and you ask, what can we prove about it? And so here there are one or two new features. You see, usually when you have a K theory, you have K of X, and then you introduce K minus Q of X. The minus sign is for good reasons, and then it's defined formally as K of X times RQ. Again, always with local compact supports. So you start off with K of X, K0, you define K minus 1, minus 2, and so on. When you have a periodic theory, eventually it comes back to the same thing, and you just have two integers. But here now you have to be careful, because when you take RQ, then we have a choice of what involution we want to put on RQ. We could put plus 1, or we could put minus 1. So we should really define space RPQ, which has P coordinates in which we put minus 1, and Q coordinates in which we put plus 1. So the involution on RPQ is minus 1 on the first set of coordinates, plus 1 on the second set of coordinates. So we have two parameters now, and correspondingly, our K theory will have two parameters. It will be KRPQ. Now, if you look what the periodicity theorem says, it's simply multiplying by the complex numbers, which is R11. That tells you can go from KR0 to K11, K22. So more generally, it tells you that KRP, Q depends only on the difference P minus Q. So although they look like two parameters of freedom, there is only one variable, which now, because P and Q can be arbitrary positive integers, but one can be bigger than the other one, this difference covers all integers. So we have a theory now that really depends on a integer variable, in principle, from minus infinity to plus infinity. But now we want to understand that better and see if we can solve more about it. Let me make a very beautiful step, which is I'll explain now in detail, because it's very simple, it's marvelous. One of those things when you see it, you say, magnificent. Let's take the RP0. That's the space RP with the involution minus 1. Inside that, there will be a sphere, unit sphere, which will be, I'll call it SP0. But be careful, it's unit sphere in dimension P, so it has dimension P minus 1. And on this sphere, the involution is, of course, the antipodal map. This is a sphere with the antipodal map and with no fixed points. Now, given any space X, we can always consider X times Y, and if you had a theory before defined for X, you define the theory for X plus Y as a new theory. Sometimes I call this space with, like cohomology has coefficients. This is a K with coefficients in Y, but that's a terminology. Don't worry about it. So now, if we do that, then of course you can also keep Y fixed, and you can multiply by R0Q as before. And if now this is one integer. If this theory was periodic in this Q, some value of Q, we say we had a periodic theory. And the question is up here: is our theory does it have any periodicity if we multiply by the antipodal sphere? So here is the beautiful theorem. You know, I used to be asked, what is the difference between a physicist and a mathematician? And so I said, well, after much thought, I said, if you read somebody's paper, if the word theorem appears, they're a mathematician. And physicists, they quite often write papers with theorems hidden in them, but they will say, well, I give convincing arguments for the following, and this is suggested. They never write theorem proof, even if they actually prove something. Here, sometimes I'm a mathematician, sometimes I'm a physicist. Here's the theorem. So here are mathematicians. And the theorem is this KR theory with coefficients in the sphere with antipodal map, let's say when you multiply everything by the sphere, is periodic with period 2p, okay? And this is true for the values p equals 1, 2, and 4. So you can get a theory with period 2, a theory with period 4, and a theory with period 8. And why is this true? Extremely elementary and beautiful. Because for the dimensions 1, 2, and 4, we have fields, which are the real numbers, the complex numbers, and the quaternions. And the multiplication by, if you take multiplication by a unit vector in each of these fields, it gives you an isomorphism. So let us consider a triple x, s, and u, where x is a point of this variable space x, s is a point on this antipodal sphere, p0, and u is a point in the space, Euclidean space, Rp, but you notice that I switch. On the left-hand side, I have R0p. On the right-hand side, I have Rp0. So the left-hand side, I'm thinking of the involution not doing anything to the R coordinates. On the right-hand side, I'm thinking of it putting -1. Now, how do we get to isomorphism? Well, you just take the multiplication. You see, x, s, u, you keep x fixed, but you multiply s and u together using the field multiplication. The s is a unit vector, unit element of the field, u is an element of the field, s times u is an invertible multiplication, gives you an element of the field again. But if you look at the way the involutions act, the involution acts on s by -1, on u it acts as +1, on s times u it acts against -1. So it switches you from R0p into Rp0. Well, that's really changed plus p to minus p, and therefore there's a shift of 2p. So if you replace this by x cross RQ, you'll see immediately it tells you the theory it replaces KRPQ is the same as where we are. Anyway, the theory ends up by being periodic with period 2p. So it all comes out of the fact that there are fields of dimensions 2, 4, and 1, 2, and 4, that you get a periodicity of periods 2, 4, and 8. And so now when we've done that, we've captured all our indices p and q. First of all, by the Bott periodicity, the pair p and q, we showed depending only on p minus q. That's still left us with a lot of integers. Now the second step is that we observe that if we replace x by x cross sp0, then we get a theory with period 2, 4, 8. So we have cut down the infinite stretch down to... I don't like this interference. So now let's examine the three cases separately. If p equals 1, then the sphere on the line is just 2 points. Okay? And the 2 points of plus and minus 1 are interchanged by the antipodal map. If you have an element in KR x cross 1, 0, well, then you think about it, it means you have a vector bundle on x cross 0, and a complex vector bundle on x cross 1, and you have a map that takes the first one to the second one antilinearly. But that's determined entirely by the first the bundle on x. The second one is just a copy. So this theory, KR x cross S1, is just ordinary complex K theory, nothing more. And we know that that is periodic with period 2. That was the Bott periodicity theorem we first started from. So that reproduces, if you like, in this context, the periodicity theorem for... Now, let's jump over to the case p equals to 2, because the interesting case is p equals to 4. For p equals to 4, the period is 8. So this theory here is periodic with period 8. And what we'd like to do is to deduce from that theory of period 8 for without the sphere, without that extra factor in it. But if you write down, compare the K theory for the pair x and x cross the sphere, well, x cross x is the same as x cross the ball, they contract. You have an exact sequence for these theories for this pair. You can write them down, and you can, here they are written down not very clearly, and there's a certain key map that appears on the left-hand side there, which shifts from p minus q to minus q, and that actually, if you examine it carefully, it turns out is multiplication by element I called e to the p. You see, a point has its own K theory. It's not, you think it'd be trivial, but it's not. The K theory of a point indexed by integers what it reproduces, in fact, are the homotopy groups of the orthogonal group, the integers and integers modulo 2 and so on. So kr minus 1 of a point is integer modulo 2, is really the sort of standard line bundle on the circle. If you square it, you'll get something on the 2 sphere, kr minus 2. If you cube it, you get 0 because nothing of this kind appears in the third component. So, and because if you take the dimensions I've chosen, p equal to 4, that first term is multiplication by 0. That means the long exact sequence breaks up into short exact sequences, which gives you much more information. And so, this is very... Can we do something to stop this?
Let's try this. See if make any difference.
I think this is just guesswork. I don't think it's any theory. We'll try and see. Anyway, so what you end up is that because you get this exact sequence like that. It's true for all greater than or equal to 3. I think I'm going to take it off altogether. I can shout. I've got quite a good voice now. But that one looks like that. It won't crackle. Okay. So the one in the middle is really the sum of the other two pieces. So basically, if you have the periodicity with period 8 there, it determines the periodicity with period 8 on the two sides. I won't go through the argument, but it's quite trivial. So when you ended up that you this KR theory is actually periodic with period 8. If you go back to the special case where there's no involution on X, this is ordinary real K theory. This is the Bott periodicity theorem for the orthogonal group with period 8, which I told you about at the beginning, and is quite difficult when you try and prove it by direct methods. This indirect method, using this real K theory, which had a different motivation entirely, gives you a very elegant, simple approach, which enables you to bypass completely all the complications that people normally meet with in studying the orthogonal group. Okay, so that's the first two parts of my talk. Explain to you why we need elliptic real coefficients, why we need a theory to handle real operators, the examples, and then the K theory, which you have to introduce, and it turned out it's a very beautiful K theory. It has a lot of advantages, even as a piece of topology. Now, let me give you the examples, applications of these things. Two examples. Here's the first example. This is an example in ordinary topology. So let's in the simplest example. So let's take X to be an n-dimensional compact-oriented manifold. Now, the first interesting invariant we have for manifold is the Euler characteristic, which is the alternating sum of the dimensions of the homology or cohomology. Now, it's a famous theorem, of course, known to Euler as well, that this Euler characteristic is the number of zeros of a generic tangent vector field on the manifold, counted with its right signs. And in particular, a corollary of that, you deduce if you have a vector field with no zeros, then the Euler characteristic has to vanish. So, for example, on the circle, going round, or a torus. Now, you also have Poincare duality in cohomology, which tells you that the cohomology in dimension q is dual to the cohomology in dimension n minus q, and in particular, their dimensions are equal. Now, because there is a minus 1 to the q in that formula, if the manifold n has odd dimension, then you see trivially that the Euler characteristic is 0, because q and n minus q appear with different signs in the formula. They cancel. So, odd dimensional manifold, the Euler characteristic is not interesting. It's 0. And in fact, on an odd dimensional manifold, vector fields with no zeros always exist. But now you can do something else, which is suggested by this formula. This was introduced by Kerver. He defined a semi-characteristic. The semi-characteristic is if you write all the cohomology groups, they cancel. But let's take only the even cohomology groups. We forget about the odd ones because actually they are the same ones again. And because we're actually going to work modulo 2, we forget about signs anyway. So we take the sum of the even cohomology dimensions and we regard it as an integer modulo 2. This is called the Kerver semi-characteristic. And it turned up in various places in topology as an interesting and unusual invariant. And I'm going to show you how it related to elliptic operators, what you can say about it. So, what is the relation with elliptic operators? Well, if you go back to our Q forms, we have the exterior differential, which takes Q forms to Q plus 1 forms. D squared is 0. If you fix the Riemannian metric, then you can define the adjoint, D star, which goes the other way, and this is defined using the Hodge duality operator, which and up to some signs, which I won't specify. The D star is star D star. So the Hodge Laplacian is what I've written there, dd star plus d star d, and that is the same thing as d plus d star all squared. You notice because the d squared is 0, and similarly d star squared is 0, you only get mixed terms. Now, let me just make a little observation here. The Laplace operator, Hodge, was introduced by Hodge, and the point about the Laplace operator is it preserves the degree of a form, because d increases it by 1, and d star decreases it by 1. So this part acts on forms of each individual degree. And his basic theorem was that the solutions of the equation Laplacian equals 0, the harmonic forms, this gives you an isomorphism to the cohomology in that dimension. This is Hodge's famous theorem. Now, if you write it as d plus d star squared, which is, I think, I was one of the first to use this, write it down, because d plus d star doesn't look a very sensible thing geometrically. It's inhomogeneous. It doesn't act on forms of a given degree. It mixes them all together. It only makes sense if you make it act on all forms of all degrees. Then you have an operator. But then what is the geometrical meaning of this, mixing up different dimensions? So nobody ever studied d plus d star, not directly, except we came across it later on for various reasons. But it has the very important property that its square is the Laplace operator, and since the Laplace operator is elliptic, d itself is elliptic, and in fact the solutions of d and d star equals 0. I mean, they are harmonic forms also. Now, you can, of course, do a little bit more refinement. You can take, because d and d star increase and decrease by 1, they preserve the parity of the degree of the form. So, I mean, they act on the same space. So they will map even forms to odd forms and odd forms to even forms. If you consider the map which goes from even forms to odd forms, then the index of this operator is, well, you look at the null space of d plus d star on the even forms. The null space of d is the same as the null space of d squared. It gives you the harmonic forms in even dimension. The other way around gives you the harmonic forms in odd dimension. The index is therefore the Euler characteristic. So the Euler characteristic is the most elementary and simplest example of an index, and it comes out as a simple invariant of a manifold. It is, of course, fundamental theorem of Hodge that the following from the topology, that if you vary the Riemannian metric, the harmonic forms don't change in dimension. So all the individual harmonic forms in each dimension do not change. The index actually is much more robust. Even if you did some variation which changed the dimensions of the individual degrees, the index will not be unchanged. But here we have stronger information. The actual cohomology doesn't change. But never mind, it is an example of an index. So Euler characteristic is the most elementary example of the index, and the formula as the Euler number is the simplest example of the index formula. And now let us just proceed by, the fact that if the vector field, the Euler number is 0 is a quite elementary piece of differential geometry. But let's see how you prove it by fancy analysis. So we suppose we've got a nowhere 0 tangent vector field, I call it psi. And using a Riemannian metric, I can dualize that and say it gives me a differential form of degree 1, a 1 form. Now, I want to use that somehow to show that the index of this operator is 0. So what we'll do is we'll first introduce what appeared in some of the other lectures, what we call the Clifford multiplication by psi. The Clifford multiplication, written in differential form language, is you just you apply it to a differential form, you wedge product with psi, making a form of 1 higher degree, and then you contract with psi, interior product, making a form of 1 lower degree. It is, in fact, the symbol of the operator d plus d star. So that is an invertible operation by the vector psi, and if you apply it to the differential form or degree up there, you'll see that it commutes with the d plus d star operator, at least modulo lower order terms. Pure algebra, it corresponds basically to left and right multiplication in the Clifford algebra. And left multiplication gives you the differentiation, right multiplication gives you the Clifford algebra, and of course left and right multiplication commute. So this is a bit of an algebraic operation which almost commutes with our operator D, and it interchanges D and D star. See, it switches them round. Now the fact that it almost commutes means that there's a topological additional piece, but because the index is changed under deformation, you can forget about that. And so what this Clifford algebra multiplication does is it identifies D with D star. Therefore, it shows the index has to be 0 because the dimensions have to cancel. So it's a very elementary piece of algebraic computation. You just use the invariance of the index under. You do use the invariance of the index under deformation, but you forget about the lower order terms. You have to deform them away. Well, the point of giving you that proof is the same similar kind of proof can be applied to other situations, which is not so simple. Anyway, let's go on. I want to talk not about the Euler characteristic, but about the semi-characteristic. So if X is now odd dimensional, let us assume it's of the form 4k plus 1. Either it's 4k plus 1 or it's 4k minus 1, and they are different. And let me tell you in advance why they're different. Because this theory is periodic with period 8, which mirrors the orthogonal group situation, the dimensions modulo 8 are each individually different. You see, so 4k plus 1 and 4k minus 1 are not the same. And they have different results, and this will apply in 4k plus 1 only. Now, if you take d plus d star from even to odd dimensions, even to odd, then with the star operator going from there, what do I want to say? Yeah, I want to define an operator acting only on even forms. I call it capital T. It's essentially got by doing d plus d star and following it by star, so it goes you first to the odd, then back to the even, and I put some epsilon outside with some sign. Don't worry about the signs. And then it turns out, if you look at the signs carefully, and here the signs are important, of course, the T now is an elliptic operator. It is real, it is skew adjoint, and its null space is, again, the sum of the Betti numbers in even dimensions. So the null space modulo 2 is exactly what we call the Kervaire semi-characteristic. So this Kervaire semi-characteristic appears as the mod 2 index of this particular elliptic operator, which has all the right properties to have a mod 2 index. So we're very similar to the Euler characteristic, but now we're dealing with semi-characteristic, but now here we're dealing with a real operator and the mod 2 invariant. Now what can we prove similar to the theorem about vector fields? Well, here there's an interesting result you can prove, which is not quite so simple as the one about single vector field. We know that if you have an odd dimensional manifold, then there always is a nowhere zero tangent vector field. But can you get two independent vector fields? Two vector fields which are always linearly independent? And the answer is in general no. So you want to know when it's possible, when it's not possible. Well, here we have a theorem. Suppose you've got two independent vector fields, xi1 and xi2. What can you do with that? Well, now you define something depending on the wedge product, xi1 and xi2, if you like the plane spanned by the two vectors, and we define an operator, invertible operator, on the even forms, again using Clifford multiplication. And I want to get rid of the dependence on the lower order term, so I've done it this way. I've replaced the operator t by averaging it with respect to the Clifford multiplication by u. So now we get something which really commutes. This is you really have something commuting with the null space, giving you an operator on the null space, and it differs from the previous one by lower order terms, so its mod 2 index will be the same. Anyway, using that, you'll deduce that the Kervaire semi-characteristic is this null space dimension modulo 2, but now the point is the null space of this operator admits the action of this Clifford multiplication, which has square minus 1, and so that means that the space is really complex, so the dimension is even, and so the Kervaire semi-characteristic is 0. So here we have a very simple application of this. If we had one vector, we showed the Euler characteristic was 0. If we're in odd dimensions, when we know the Euler characteristic is 0, we look at the semi-characteristic, and if we have two independent vector fields, we prove the semi-characteristic is 0, not 2. So there's a very analogous result. But it's not true in dimensions 4k minus 1. So really it does depend on these parities of dimensions. By the way, this didn't really use the two independent vector fields. It just used the fact that you had an oriented two-plane spanned by them. So if you had the slight differences. So that's what I've spelled down there. If the Kever semi-characteristic is not 0, you can't find two independent vector fields. So what's the examples? Well, let's look at the spheres, odd-dimensional spheres. S5 is of the form 4k plus 1. The cohomology is just in dimension 0 and 5. The even cohomology only in dimension 0. So the Kever semi-characteristic is 1, not 0. So you deduce you cannot find two independent vector fields tangent to the 5 sphere. If you went down to the 3 sphere, which is 4k minus 1, the 3 sphere you know is a Lie group. It's just the unique quaternions. A Lie group is parallelizable because you can just go from identity and parallel translate everywhere. So you can get 3 independent vector fields. Actually, if you have 2, the third one in dimension 3 follows by orthogonality. But anyway, on the 3 sphere, you do have independent vector fields. But the theorem doesn't apply in the 3 sphere because that's 4k minus 1. So you see, it works nicely. So the 5 sphere, 9 sphere, 30, all these spheres are okay. 7 sphere. 7 sphere is not of the form 4k minus 1, 4k plus 1, it's the form 4k minus 1. Now the 7th sphere is not actually a group, but it's nearly a group. You can take the unit octonion, the Cayley numbers, and they act by Cayley octonion multiplication on R8. So it's again parallelizable, and you have a lot of vector fields. And similar results for other spheres, we can ask questions about vector fields on spheres. So it's quite subtle, and the results are best possible in terms of working on certain dimensions, not in other dimensions. Also notice the following fact. Let's consider S5 and consider the map by the quotient by the antipodal map, which gives you rise to the real projective 5 space. It's double covering. Now the Kever semi-characteristic of the 5 sphere is 1 because homology is only in dimension 0, and the real projective space it's integral cohomology. There are no ranks. They're the only torsion except in dimension 0. So its characteristic is also 1. So both these spaces have semi-characteristic 1. Now, it's simple. If an invariant was given to you by a formula which is local, by integrating some expression, then when you go to a covering, you multiply by the degree of the covering. Here the degree of the covering is 2. So theoretically, anything given by a local formula would be 0, and worked upon 2 would be 0 upstairs. So this shows you that k cannot be given by a local formula. Unlike the Euler characteristic, the Euler characteristic does multiply on the coverings, is given by a local formula, the famous Gauss-Bonnet theorem. So the semi-characteristic is and the index theorem in general gives you an index, an integer, which can be calculated by a complicated integral in terms of the curvature. But these mod 2 indices, this example shows you, cannot be calculated by integral formulae. Even though in this case it comes by reduction from integer to dimension, it cannot be given by an integral formula for this fundamental reason that it doesn't have the right behavior under finite covering. So these mod 2 indices are much subtler things, but as you see they are quite interesting. So that was the first example. My second example is going to be a holomorphic analogue. Now, in one of the earlier lectures today, you heard stories about Chern-Simons theory in dimension 3, and then the holomorphic analogue with holomorphic Chern-Simons in complex dimension 3. This is in the same spirit. We go from real manifolds to complex manifolds, and so here let me tell you what we can do there. Suppose we want a holomorphic analogue. So we start with a compact complex manifold of complex dimension n, and we consider the holomorphic Euler characteristic, that's to say the alternating sum of the sheaf cohomology groups of the sheaf of holomorphic functions. That's called, in algebraic geometry, that's called the arithmetic genus, essentially. It's a very interesting, much more complicated expression than the Euler characteristic of ordinary topology. And the index theorem, which in this case is the Hirzebruch-Riemann-Roch theorem, gives you a formula for this in terms of the famous Todd polynomials in terms of the Chern classes. This is a special case of the general index theorem, and it's a complicated and beautiful formula, and it can be given by integral expression. This is the analog of the Euler characteristic. Now, how about the second part? Well, you see, just like we had Poincare duality for a real manifold in cohomology, we have Serre duality for sheaf cohomology, and Serre duality is very similar, so that HQ of x with coefficients in the sheaf of functions is dual to Hn minus q, n being the complex dimension, x with coefficients not in the sheaf of functions, but you twisted by the holomorphic n-forms, which is gives you the canonical line bundle. So, see, in the real case, you would have the real line bundle, and if the manifold is oriented, that's trivial. So that doesn't appear. But here it appears, and that's an important differential fact. If manifold is, for example, Calabi-Yau, then the canonical bundle is trivial. Then you simply have without the twist in it. And if the manifold is odd-dimensional, then just as before, the Euler characteristic would be 0 if the manifold is odd-dimensional. In which case, you could define the holomorphic semi-characteristic by just analogy. Just take the sum of the even dimensions, modulo 2. And the theorem result is the same sort of reason before. This is a mod 2 index. That means it will have stability under deformations and all that. If the dimension of n, which is the complex dimension, is again of the form 4k plus 1. So it's a very analogous result. The proofs are essentially by the same sort of, the verification is very similar. It's the holomorphic analogue of the Kerber semi-characteristic, but it's much subtler because it deals with sheaf cohomology. Now let me take a special case of that. Supposing that we have, or special case and also generalization. The reason I wanted to move away is you see that in the previous case, the first interesting dimension was 5. So the first interesting dimension of this would be 5 complex dimensions. That's a bit high. I would like to get down to 3, but I can't get down to 3 because the orthogonal group doesn't have a right behavior in that way. But if I shifted by 4, going from the orthogonal group to the symplectic group, these things switch round. So I want to switch, and you do that the following way. Suppose we have a holomorphic bundle now, not just the functions, on X. And supposing that it has the following property, it has a skew-symmetric bilinear pairing, E tends to E into the canonical line bundle, which means really that the canonical bundle E is isomorphic to its dual twisted with the canonical bundle. Now in the Serre duality, you get the relationship between E and E star tends to K. Really, that's their duality. Sorry, I think I didn't specify that before. Yeah, I didn't have a bundle before. I had only the functions. But if you have Serre duality with a bundle, here it is. So the cohomology HQ with coefficients in the sheaf of sections of a vector bundle is dual to n minus q of X with coefficients in. It should be E star tends to K. E star tends to K. But if you have a skew bundle, E star tends to K is also E. And this will tell you then that the Euler characteristic of X with coefficient in E is 0. Therefore, the holomorphic semi-characteristic we can define and introduce. And this is an interesting invariant in the cases when the dimension of X is congruent to 3 mod 4. So it will include 3-dimensional complex varieties. The reason is I brought in this skew pairing in E, that's hidden in the symplectic group. Now, some example, I'm specializing down. Take n equal to 3. Let me take X to be complex vector 3 space. Now, in complex vector 3 space, it's not a Calabi-Yau. The canonical bundle is the bundle of Chern-Clauss, the line bundle to be 4. Chern-Clauss is 4. Suppose I have a rank 2, just 2-dimensional vector bundle on X, on CP3, with first Chern-Clauss 0. So really the group is SL2C. In SL2C, you have natural skew-symmetric form. So on E, you have a natural skew-symmetric form, and if you take E and twist it by the square of the natural line bundle, which I describe E bracket 2, then E bracket 2 E bracket goes into the O4, which is the canonical bundle. And therefore, the cohomology in dimension 0 of CP3 with coefficients in E2 plus the cohomology in dimension 2 of CP3 with E coefficient E twisted by 2, this is a topological invariant of E, but taken modulo 2. So here we have a very special situation. Here's the general situation. I have a rank 2 vector bundle with first Chern-Clauss 0. Then I define a topological invariant of the bundle, which you can calculate holomorphically by calculating these H0 and H2, taking the modulo 2. That's a topological invariant, which means that if you vary the holomorphic structure on the bundle in a moduli space, then the dimensions might change, but mod 2, this sum does not change. And that's a topological invariant independent of the holomorphic structure, which I studied with Elmer Rees, and we called it alpha of E. And actually it turned out rather nice. So if you ask...
Are you arguing this
Yes? Well, it's a topic. Well, both. So let me say it's the following. If you look at CP3 and you ask for the classification of topological classification of vector bundles on CP3, if the bundle is dimension line bundle, it's trivial, it's just given by the first Chern class. If it's dimension 3 or more, then you're in the stable range. It's given by the K theory, and is in that case determined by C1, C2, and C3. If it's rank 2, it's just in the middle, then his situation is more subtle. And now I tell you the answer. So in for rank 2 bundles, well, if the bundle, sorry, I don't mean SU2. If you have topological classification of U2 bundles, because that first term class is allowed, is it? Then you have two cases. Either the first Chern class is odd, in which case invariants are just C1 and C2, or the first Chern class is even, in which case you have C1 and C2, and you have this alpha, integer mod 2, which is got by, you first, because C1 is even, you can move it up and down to get to the case we had before, SU2, and so you have additional mod 2 invariant. This is the complete topological classification of SU2 bundles or U2 bundles on CP3, and C1 and C2 are the Chern classes. Alpha can be defined as the mod 2 index of a certain Dirac operator, not using the complex structure, just using it. And that's the first statement. Second statement is that holomorphic bundles exist for all these invariants. Any set of invariants, any pair of integers C1, C2 with C1 odd, or C1, C2 and alpha with C1 even, for all of these, holomorphic structures exist. There are vector bundles with holomorphic structures which have these invariants. So this means that if you were an algebraic geometer studying vector bundles of rank 2 on CP3, you start off by fixing a topological type. Because usually if you do it by differential geometry, you fix the topological type once and for all. On that you put connections which are integrable, you do gauge transformations and so on. But each topological type is distinct. There are many components. And usually the components are determined by the Chern classes. People tend to assume that's all you need. But in fact, in this case, you need more. There is C1, C2, and alpha. And you have, for given C1 and C2 with C1 even, there will be two different components and two different moduli problems. And this might be of interest to those who study moduli problems. For example, if you take alpha not 0, then that family can never deform down to a trivial bundle. I mean, for example, if suppose C1 and C2 are 0, alpha is not 0, this is not the same component as the trivial bundle. The trivial bundle, for example, is always a very bad bundle. It's always a very degenerate bundle. It gives rise to singularities. You like to keep away from it. And if your alpha is not 0, then you keep away from such things. And that might be, would mean that it would lead to a simpler moduli space. It would be an easier one to calculate with. So it should be a rather interesting one to take into account. So this, I should say, this is in a paper of mine with Elmer Rees. I'll give you the reference in a minute. And we started off with the problem, just a general question, which topological vector bundles on CP3 can be given a holomorphic structure? Nobody knows, really. There are sort of some natural conditions which are trivial, but in this case, if the bundle is of large rank, then it's easy because they're stable and the K-theories are the same whether you work with algebraic geometry or topology. For line bundles, it's trivial, but in the middle, it's unknown. And the first non-trivial case, really, is the case of rank 2 bundle on CP3. Rank 2 bundles CP2 are determined by C1 and C2. This X alpha only appears in dimension 3. And so we knew about this invariant, and then we made examples, constructions, found that there was a holomorphic bundle with arbitrary triples C1, C2, C alpha. So we got this very indirect proof that every topological bundle has a holomorphic structure. The question in general of which topological bundles has holomorphic structures, is one of the big unsolved problems in algebraic geometry, and it's related to the Hodge conjectures and so on. So it's a very difficult question. But in this particular case, we managed to solve it by using this rather subtle mod 2 invariant and the explicit constructions which you can make for construct algebraic bundles by using algebraic curves. Okay, so now let me give you some references. So I've got 5 references for you. The first reference is the paper I wrote on this real K theory, and no, sorry, this is the theory about the KR theory, just defining it, give it properties, proving the periodicity theorem, proving this nice periodicity module 8, getting all of that is contained in this paper here, which is a self-contained paper, really to be read by topologists, if you like. Then the seem to have left out. Oh yeah, I left out one reference I should have put in somewhere here. Forgotten. Maybe I gave it before. There's another reference. This is my paper with Singer on the index theorem for elliptic operators in the Annals of Mathematics, part 5. There are papers 1, 2, 3, 4, 5, and the last one deals with real operators and shows how to use these reality conditions in the index theorem for families. Then in paper number 2, this is the index theorem for skew joint Fredholm operators, which I wrote with Singer. Is a very systematic use of studying these questions of these skew joint Fredholm operators, these mod 2 indices in all dimensions, and that's related it to the Clifford algebras in all dimensions. Clifford algebras underlie the Bott periodicity theorem in topology, and actually we got a new proof of Bott periodicity for all the real groups hidden in this paper, a totally different approach. It's written in terms of rather abstract Hilbert space operator theory, and it's different from other approaches. But it's systematic for all dimensions. Then the third paper is a short paper I wrote with a very long title. I mean, it's vector field and manifold, and it's published by it's a talk I gave in the Academy of Sciences of North Rhine-Westphalia. And they produced a little publication, and the first bit says something Arbeitsgemeinschaft or something in a long German word telling you it's somewhere in their annals of their publications. And this is meant to be a general talk, so it's an expository talk. It's a bit like what I started off with, talking about Euler characteristics, one vector field, two vector fields, but a few more examples of that kind, showing you what you can do to relate vector fields and the topology, and asking how many independent vector fields there are, and so on. It's a reasonably general account. A much more extended account is my number 4, my paper with Johann Dupont, which is called Vector Fields with Finite Singularities. And that one, I'll tell you what it's about. It contains a very general theory about the operators, skew joint operators, mod 2 indices, etc., all the dimensions of modulo 8. But it does a bit more than that. If you have a Euler characteristic, a manifold with a vector field, I told you that the Euler characteristic is the number of zeros of the vector field, counted with a suitable sign. And the question is, if you take manifold with more than one vector field, several independent vector fields, and you assume that they are linearly independent everywhere except at some points, then can you associate to each point some quantity which you sum it up and will give you these mod 2 indices and so on, things like that. And in this paper we do a systematic account of that. We show if you have vector fields independent everywhere except at finitely many points, at each point you can define something quite complicated topologically. You have a theorem which says the sum of all these can be calculated by some analysis. It may be, in fact, an integer modulo not just 2, but modulo high power of 2. And a very systematic account of all those is in that paper there. Then my paper with El Maurice is the last one, is the one about this rank 2 bundles on CP3. It's quite a short paper, but it uses this mod 2 index in the holomorphic context. And then, of course, my previous lecture, I did mention the other example I haven't mentioned today of this mod 2 index, which is to do with the square root of the canonical line bundle on a Riemann surface. That's the sort of dimension, complex dimension 1 case, and this is the complex dimension 3 case, and that was interesting also as well. But this is one bit up, and in some sense, unexpected connection of the algebraic geometry with the topology in that example there. So I think I'll stop there.
So if you start with regarding your question earlier today,
yeah.
If you start with a curve in CP3 and
yeah.
use a set construction to get the SU2 bundle, what is the alpha?
Well, it depends, of course, on the curve. I mean, I had to.
How do you see that from the curve?
well, the curve has to have the right kind, of course. It has to be one where the normal bundle has the right degree to extend and so on. I don't think I ever calculated that. Obviously, for a straight line, you can work it out. And it's interesting. I mean, an interesting calculation. Some of the examples are obtained by using some curves, I think. But I haven't gone back to that paper for a long time, so it's a good exercise for you young guys like you. It's quite fun to see. I mean, if you to see if you can calculate, as I mentioned something else before, that this holomorphic analog of Chern-Simons theory in dimension 3 should be related to things like curves in dimension 3, like knots occur in real theory. And this invariant here, might have some analog in some things there. But I mean, I think it's well worth investigating and examining further if you can rate it to something to do with the curve. Yes, it must be possible.
So also in this case, the free flow do not need to be projective, right? Just complex free flow.
Do they
need to be K? Okay.
No. It doesn't need to be complex. I mean, you use the Dirac operator. It doesn't need to be a complex manifold. Except the SU. But you see, I use an SU. It depends what you want to assume. No, I mean, you have the Dirac operator. It has to act on a symplectic bundle, basically, to get that shift from the orthogonal group to and the SU2 happens to be the same as SP1, and that's a symplectic bundle. Then in that context, you write down the Dirac operator. But of course, you can't calculate. If the manifold is not holomorphic, how do you calculate the number of solutions of the Dirac equation? Okay, so it's not very computable. The advantage of rating it to a complex manifold is that you convert it into algebraic geometry, where there's much more machinery, where you can hope to calculate some of these dimensions explicitly. At least it's more reached to algebra in some sense. But it doesn't. No, you haven't. If you have a non-Kähler manifold that you like, you go ahead.
So it reduces to a bundle over the four manifold.
Yes, you're quite right. If it was three-dimensional twistor space, then a holomorphic bundle would get down to a self-dual bundle on the four manifold. And yeah, good question. I mean, but see, I worked at these different stages of my life. I didn't talk to myself across time. Forward time is difficult. Backward time is probably easier. So yeah, it's an interesting question whether what this corresponds to yeah, I hadn't thought about it. It should be. Well, let's see it. It makes perfectly good sense. So it must be something which you get on the for a self-dual for an instanton. Yeah, it should have some mod 2 invariant. What can it be? I don't know. Well, it might be, No, I guess because sorry, I tell you the answer because you see, if you have this twistor correspondence, then we know that self-dual bundle corresponds to holomorphic bundle upstairs, and we know that solutions of the various linear equations that below, like the Dirac equation, correspond to sheaf cohomology upstairs. So the sheaf cohomology upstairs, the H1 corresponds to sheaf cohomology down to solution. Now, I took the even dimensions, but because of the duality, I could just as well have taken the odd dimensions. So I could take H1 and H3. H1 will be solutions of something like a Dirac equation coupled to the instanton with some coefficient bundle. Some linear, it'll correspond, and then the H3, by duality, is really an H0, that is possibly 0 in some cases. So anyway, it may correspond to the index of a Dirac operator coupled to the instanton, and perhaps coupled to some auxiliary bundle. That's a good guess. And it may be then that will correspond to the mod 2 index on the four manifold. See, there are these mod 2 indices in different dimensions. Although that's even, it worries me a little bit. 4 is very hard to avoid, difficult to make it an odd number. And even if you put symplectic bundles in, that doesn't change. It might be 0, but anyway, that's a good question. It might be nice to follow that through. I think I sort of sketched half the way to calculate the answer. The answer is computable in 5 minutes. Well, 10 minutes.
Other questions?
got two questions. The first question is that for the odd manifold, you may have some kind of lower zero vector fields.
Yeah.
And you may we have lower zero vector fields. Okay. And is it possible to conjugate the equivalent classes, the number for such lower zero vector fields?
Well, I mean, the question of trying to work out what is the maximum number of linearly independent vector fields you have a manifold is a classical problem in algebraic topology, and Frank Adams solved it for the sphere, really very nice numbers to do with Clifford algebra and so on, and it fits into this framework quite well. Let's say finding the maximum number, and of course once you've got a set of vector fields independent, you can ask for the homotopy classes of these things. It's a topological problem. Yeah, these you can ask such questions, and I mean, there are a lot more information. I gave you just the simplest example, but this paper of mine with DuPont has many much more complicated ones, involving many vector fields and singularities and rather funny theorems that you can prove about them. First question. What was the second question?
Second question is that you define the Laplace operator.
Yeah.
Another one, okay. This is for the simplicity of homology. The complex, you also have the boundary and the co-boundary operator if you define the inner product on the simplicity complexes. And you define the similar the Laplace operator. That one, the kernel is also given the homology. Okay.
Yeah.
And I wonder that whether have the general operator, how to define the other operator, like elliptic operator, how to define on this kind of discrete.
Well, I mean, the question of how you define elliptic operators on combinatorially is something is quite straightforward. You can define the Laplace operator. That's quite easy. But much more difficult is to define things which are matrix valued, like Dirac operators, because the vectors they act on, like spinors, are much harder to define combinatorially. They don't know any sensible definition. Even the differential form. I mean, what you can define is a Laplace operator on scalars. If you want to apply the differential forms, it's not quite clear what a differential form. I suppose you can talk about functions on the edges. I suppose a cocycle. And so probably you can do something like that. You can probably that's been done. There are people like Dodchuk who studied Hodge theory on triangulations of manifolds, and you can prove that these are converge as you subdivide the triangulation. These will converge to the Hodge Laplacian. You can do all that, but there are some difficulties if you try to introduce things like spinors. That is really you're into trouble. The Dirac, nobody can define the Dirac equation, I think, on a lattice. Physicists would like to, but they don't know how to do it. You need 2 copies of the lattice or something like that. It's quite fundamentally difficult. So that the basic analysis is okay, and some of the elementary geometry goes through, but the harder geometry, I think, can't be done. Whether you get any mod 2 index problems combinatorially, maybe you might still be able to find an example of that. So, for example, the semi-characteristic, the homology one, is a topological homological invariant, and those things are certainly definable combinatorially. So it must be possible to do that one. Yes, I'm sure that will exist.
I'm thinking, what is the consider even number of cells, mod 2 or 4? You don't just look at that.
Just look at you want to go back to the chain complex. Yeah. I mean, we know that in a finite complex, the Euler characteristic is also the alternating numbers of the cells, going back to the chains. But whether you can get a semi-characteristic by only counting the even cells, would be pretty doubtful. I'd be very suspicious. But maybe good question. Some young chaps could try. Why not? I mean, you can. We even dimensional homology has some invariance, mod 2. So perhaps something to do with the just counting cells numbers might make sense. Except, of course, Poincare duality is a bit tricky with the triangulation. It relates a cell decomposition to the dual cell decomposition. You must take triangles and then take the duals. You put a point in the middle of each triangle and so on. The Poincare duality doesn't really work on a given triangulation. It changes one triangulation with a dual triangulation. So this is already a little suspicious, because I wanted to use that to cut down to half. Anyway, good question. Needs more thought. I'm open-minded. It might be possible. What do you think?